Okay, so far all the students have done is copied the notes from the first page, so if you're watching this on video.
Teachers, please excuse the interruption. The students that were testing this morning in the auditorium have been released and should be in their classrooms at this time. All the students from the auditorium should be in their classrooms. Thank you.
Okay, so once again, if you're watching this lesson on video, go back and print out the notes and you'll have all this. And then we'll talk about it in just a moment. Yes, ma'am?
L minus P for the Q, where's the L?
Huh?
P equals success.
Oh, is that like an L minus?
Right here? No. If we look at this, it says Q represents failure. Well, the probability of failure isn't that 1 minus the probability of success. So some books will use Q here, and some books will say 1 minus P. So since these are equivalent, that's why we can have either. And I'll talk you through the whole thing in just a second. Okay, so binomial probabilities are what we're going to be looking at. And binomial probabilities can be found if we are given in a binomial experiment. So what are our parameters for a binomial experiment? First of all, we have to have a situation where there are repeated trials. Every trial has to have exactly 2 outcomes, either success or failure. Okay? So if I went home today and Santa brought a bag of peanut M&Ms and I wanted a green one, I can reach in and either get a green one or not get a green one. So there's success or failure there. The trials are independent. So one experiment would not affect another, and each trial has the same probability of its success. So those are the 4 things we're looking at. And if we can check off all 4 of those, then we have a binomial experiment, and we can use binomial probabilities. All right, now this is the formula we're going to use in just a minute, and I'm going to show you where it comes from. It's a combination of n choose k, if k represents the number that we're selecting for our success. P is the probability of success. Q is the probability of failure. We raise P to the K and Q to the N minus K. And I'll show you how that works in just a second. Where? Oh, this is N. It does look like an H, but it is an N. It's an N with a big stem.
Now is that like all together?
All this is together, yes.
So it's all like
everything in the box is one big product. Everything in the box. Okay? Okay, so let me talk you through a little bit right here, and we're going to set up a scenario, and we're going to determine whether we can use a binomial experiment for this. There it is. Okay, my first example. We're going to take a deck of cards. We're going to shuffle them. Turn over the top card. Then we're going to put it back in the deck and shuffle again and turn over the top card. And repeat this process until we get an ace. And our random variable, we're going to W, represent the number of cards required. Now, does this satisfy the conditions for a binomial experiment? Are there repeated trials? Yes. Are there exactly 2 outcomes? Either I draw an ace or I don't draw an ace. Are the trials independent? Yes, because I put the card back every time, didn't I? Does each trial have the same probability of success?
Yes.
Yes. Each time I put the card back, so the probability of choosing an ace is 4 out of 52 every time. So that is an example of a binomial experiment. Okay, stick with cards, and let's say we shuffle a deck of cards, and we turn over the first 10 cards at a time. Could Y represent a binomial variable if Y represented the number of aces we observe? Would this be a binomial experiment? No. Why? What part does it fail?
There's more than 2 outcomes.
Number 4? What does it fail on number 4?
Representing. You put up the top 10 in number. Can you say that again?
Yeah, I didn't hear you. Kind of.
The scenario?
Yeah.
Okay, the scenario was we're shuffling a deck of cards. We're turning over the first 10 cards, one at a time. If we let our random variable represent the number of aces we observe, will this give us a binomial one at a time? Are we putting them back? No, they're not independent. We're not putting them back. So can I use a binomial experiment on that? No. Okay, here's another one. Genetics say that children receive genes from their parent independently. Each child of a particular pair of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X represent the number of children with type O blood. So, does that random variable, would that be a binomial distribution? Yeah. The situation has repeated trials, because how many children? 5. Every trial has exactly 2 outcomes. The child either has type O blood or does not. The trials are independent of each other.
Yes.
The blood type of one child does affect the blood type of the next. Each trial has the same probability of success. 0.25. Yes, it does. Okay, so let's take that scenario and let's work with it. Okay. So, we're dealing with the toe blood type. Example. Okay, so brief synopsis. We said the probability of the child having type O blood was 0.25. So what would be the probability of the child not having type O blood? 0.75. The complement of that, right? And in this case, the family is having 5 children. So the number of repeated trials is 5. Okay, so first thing we're going to do is old school. Old school way of finding the probability that we have no children with type O blood. So it would be the probability of a failure times a failure times a failure, and a failure, right? It would be having 5 failures in a row, which is not nice to talk about your children in terms of being failures. But that's what we have. So if we were, yeah, you get it. Oh, was she even meaner?
I didn't say anything.
Did she call you a failure? Who was? You? Wow.
That was Garrett.
I know. Every day y'all are mean to her. I'm gonna be nice. All right. So probability of failure 0.75 times 0.75 times 0.75. Somebody please tell me how I could do this quicker. Thank you. 0.75 to the 5th. Okay, so I could have written it much easier like this. 0.75 to the 5th. Okay, and what does this give us?
0.2373046.
0.2373. I'm good with that. That's good enough. So the probability of those 2 parents having no children with type O blood would be 0.23743. Okay, now let's say what is the probability that they have 1 child with type O blood? So let's let the first child be a success. And then the rest would have to be failures.
At least one.
At least, you know what? At least they have 1. So, what's the probability of that first one being successful? 0.25. And then the rest of them would be 0.75. So, it would have been easier had I written this way. 0.25 to the first and 0.75 to the fourth, right?
Yes.
And we don't even need the first there. Okay, now let's say the first child was a failure, but the second child was a success. Is there any difference? No. Because when I multiply, the order doesn't matter. All I'm doing is switching these two. So once again, I have just 1.25 and then 0.75 to the fourth. Okay, what if the third child was the success? Oh, the middle child. Something good happened to him.
Oh, thank you. Hey.
Hi, here we have some middle children in the crowd. Same thing. What about the fourth child? Okay, how many people are annoyed because we see the pattern? And we're just frustrated at this point. Me too.
Wait, just keep going that way.
All right, here we go. The fifth child. This case, the baby, is finally successful. So, these are all the different ways that we could have had one child with type O, right? So what would we do with all of these probabilities? Add them up, wouldn't we? What's a shortcut to repeated addition? And aren't there 5 of them? So I'd just do 5 times 0.25, 0.75 to the fourth. Isn't that beautiful? Okay, now, the reason this is beautiful is it ties back into that formula we just looked at. That formula was this. C of n, k, p to the k, q to the n minus k. Now, what we have in this case is we have the combination of, how many children are there? 5. How many do we want to have type O blood? 1. What is the probability of success? 0.25. And how many did we want to be successful? 1. What is the probability of failure? So if 1 was successful, how many were failures? 4. Is this the same thing as this? It is. So instead of having to do all this work, when we want to know the probability of exactly 1, we can use the binomial probability formula, which is the combinations of n choose k, p to the k, q to the n minus k, which is a lot nicer. So when we punch this in, do we get the same thing as when we punch that in? And either way, did you get approximately 0.3955? Okay, so what would it look like here for no type O? This would be the combinations of 5 choose 0, and then 0.25 to the, how many successes did I want? 0. 0.75 to the fifth. Are those exactly the same thing? Yes, they are. Because the combinations of 5 choose 0 is 1. So this becomes 1 times anything to the 0 is 1. So it's 1 times 0.75 to the fifth. Okay. Questions about that? Do we see how the formula works? Do we see how it's a nice little shortcut? Yes, ma'am.
So one of them was typo. That was in front of the probability of one of them being typo.
This is one child with type O blood.
Okay.
So, yes, I should have written it out like that. This is the probability of one child with type O blood.
And so you get the probability of any of them having type O, or being a success or whatever, of each of them, and you multiply it by 5 because that's the number of kids.
Well,
I guess.
I was showing you the long way
Mm-hmm.
so that you could see why the formula works.
Right.
Yeah. Yep.
So that's
We
why-
multiplied it by 5 because there was 5 different positions for that one successful child.
Okay.
Okay, what if instead, oh, yeah, exactly one child with typo, but I actually had that written. So that is what we just said. The combinations of 5, choose one, of 0.25 to the first, 0.75 to the fourth, which is exactly the same thing we got just a second ago. Okay, any questions? All right, so let's try a couple more examples. Okay, here's a scenario. And you were asked to find the probability of getting exactly 3 correct answers out of 5 questions on a true-false test. Okay, first of all, does it pass muster? Is this a binomial experiment? Yes, it is. Okay, if we come back and look at our, does the situation involve repeated trials? Yes, we have 5 questions. Does every trial have exactly 2 outcomes, success or failure? Yes, we get it right or wrong. Are the trials independent of each other? Yes. Does each trial have the same probability of success? Yes, so it does. This is a binomial probability problem. And so what we can do are the combinations of, can you see this dark blue?
Yes.
Okay, the combinations of, what's N? What are the number of trials? 5. And what's K? 3. 5 choose 3 of, what is the probability of success? 0.5, because it's true false. And how many do I want to be successful with? 3. So if the probability of success is 0.5, what's the probability of failure? 0.5. And how many will I miss? 2. Okay. So find that probability. As I look for my answers. There we go. Ooh, shame on me. I forgot to write my probability statement first. I'll sneak it back in there. Okay, did you guys get 0.3125?
Yes.
So the probability of getting 3 out of 5 correct is the combinations of 5 choose 3 times 0.5 to the third times 0.5 to the second. And so this would be the probability of that occurring. Okay, now let's look at our second scenario. Our second scenario tells us that about 13% of the general population is left-handed. Out of 20 randomly selected people, about how many people would you expect to be left-handed? So if we had 13% of 20, would expect there would be about 2.6 left-handed people. So we would really need to round down and say 2. Approximately, because we can't have part of a person. Okay. Now B says, what is the probability that exactly 2 of 20 randomly selected people are left-handed? So this is a little different. This says, what would you expect? This is what is the probability that exactly 2 randomly selected people are left-handed. So is this a binomial experiment? Yep. We are choosing 20 people, so we have repeated trials. We have our probability of success, which is not going to change. They are independent of each other. Whether or not one person is left-handed doesn't affect if the next one is. Okay, so we would say the probability of 2 of 20 being left-handed is the combinations of, what would it be? 2 choose 20. And what is the probability of success? 0.13. And how many successes? 2, and failure. And how many failures? 18. So what would it be? Very good. Okay, now, when we're looking at a binomial probability, this is telling us how likely something is to occur, rather than what will actually occur in our sample. It's giving us a likelihood of something happening. Not exactly what will, but it's a likelihood. It tells you how likely something is to occur rather than what will actually occur in the sample. Okay, we have a little over 20 people in this room. Raise your hand if you're left-handed. 1, 2, 3. Ooh! That's really good. That's pretty close, isn't it? So we got lucky. First period, we had all the left-handed people raise their hand, and it looked just like this. Nobody had their hand raised. So, raise your hand if you have left-handed people in your family. All right, that increased. Really?
Yeah.
Except for you? Huh. Interesting. And this one? Okay. My next question. My next example. Example 3. We have a 5-question multiple choice quiz. Unfortunately, it's written in German, and I don't know German. So my answer choices are A, B, C, and D. What is the probability that I would get 4 out of 5 of these correct? Okay, you try.
How lucky should buy a lottery ticket? 4 to 5.
Well, when you look at my probability, I'm in trouble.
Are you serious right now? Nice,
Guys, is it binomial? I've got 4 answer choices, though.
But you're just doing correct.
Oh, you're just, okay. You're right. When we're looking at this, we either get it right or we get it wrong. We don't care how many answer choices there are. The answer choices give us the probability of success, doesn't it? Good. So did you do the combinations of 5 choose 4? And what is my probability of success? 0.25 to the 4th, and then 0.75 to the 1st. And so my probability is not good. The probability of me getting getting 4 out of the 5 correct is terrible. Now, what if I had said here, instead of 4 out of 5, I'd said at least 4 correct? What would I have to do in that case?
Out of how many that probably would.
Good. Add the probability of exactly 4 with the probability of exactly 5. That's if I said at least 4. We're not going to do it, but you would do the probability of 4 plus the probability of 5. Good. So that leads us to this problem. How would we find the probability that we got 2 or less correct? So what would we have to do on this one? Probability of 0, plus 1 plus 2. All right, did you get what I got? Now, I told you this was going to tie back into, oh, hold on. One last one. What if I ask you for the probability of 4 or less? Okay, so we do 1 minus the probability of 5. Good. So if we can look at a complement and it gets us there faster, especially on your homework tonight, please do it that way. Don't add up 1, 2, 3, and 4 when we can just do 1 minus the probability of 5. Okay? All right. So let's tie it back into Pascal's now. I promised here I am to deliver. Now, if I ask you for this coefficient here, for this 5th row, what we would do is the combinations of 5, and what exponent do we want? 4th. And it would be this to the 4th, this to the 1st. So this, what is the combinations of 5 choose 4? 5. So this ends up being 5 times 3a to the 4th, b to the 1st. Is that the same thing I had right here? Now, the reason this would have been helpful, and you're about to be mad at me, I know that. I'm all right with it. On this problem right here, when you were asked to give me the coefficient of x to the 8th, what could we have done in the expansion of this to the 12th? It would be the combinations of 12, choose 8, x to the 8th, and 4 to the 4th. Without expanding Pascal's at all. Okay, so if you're on my math team, this is really important to you, and you're not going to forget this.
Is this going to be on a test or quiz?
This is one of those cool things that I sneak in for bonus. It might be on the real test. And that would taken us straight to this answer. And this problem is exact off this that we did the other day.
Miss Wendy, are we going to get a test before?
Where do I get this?
All over?
Where do I get the 4? Okay. If this asks me for the 8th one, the 8th goes here, and every time these two have to add up to n. So if this is 8, that has to be 4. Okay. What now?
Oh, nothing. My question was answered by a fellow student.
Awesome. Okay, so here's a you try. Okay, in the binomial expansion of 2x minus 3 to the 7th, what is the coefficient of x to the 4th? In the binomial expansion of 2x minus 3 raised to the 7th, what is the coefficient of x to the 4th? Be careful, because this is minus. That minus goes with the 3. Don't let it trick you. Did you get negative 15,120?
Oh, yes. Yeah, I got that, but with like 7 more zeros.
Weird. Did you put the x in your calculator? Don't put the x.
Oh.
You're looking for the coefficient. Your calculator has a value stored in for x. Like your calculator thinks that x is 10.
That's what it said.
So
what
binomial
do you put in instead of x? Just 2?
You don't put an x.
You just put 2?
You're just putting this part in your calculator. Everything but the x.
Somewhere she said find x.
So what we just did with binomial probabilities is totally different than this, except it's got the formulas.
We can find any of the terms in Pascal's triangle using that binomial probability formula.
Okay, but you plug in different things for the E and
Yeah.
Okay, so you put the first term where P would be and the second term. And then
Yep.
sum that
It's your A and your B.
like 1, 2. And then you put. There were ones that I had used the book for.
Those.
There were 8 like the given examples.
Okay, you have a worksheet for homework?